Okay, so hopefully after the arc length, there are one small section about tangent, and then actually that will be the end of the calculus in polar. The next section is about the conic section and conic section in polar. So I hope we can finish until conic sections, and the rest will be continue next Monday, and I will also having the maybe some practice and exercise, and also giving you maybe additional video to watch for some practice. And I think we can have our first quiz next Friday, next week. So the topic will be chapter 10, includes from the parametric, the polar, and also the later the conic sections.
Next Monday we have. Next.
Yeah. Okay, so it will be next Monday. The quiz will be next Monday. Yeah, I forgot it's 2 to 8, right? Yeah. Okay. Okay. So let me continue a little bit for the small section of the tangents in the polar. Okay, remember that we can write our x and y in terms of r and theta. We can convert Cartesian to polar. We can write r in terms of a function of theta. So this is what we can write. Okay. Now, if we are going to have our tangent, which is dy over dx, based on our understanding and our definition in the parametric one, this is precisely using the chain rule. We can have these connections, right? And then we can also can get the each of the derivative from x and y. Okay, and then we can use those results into our equation. Okay, so this is our tangent equations in terms of polar. So basically, you will have, for example, you have some polar equation, maybe 1 plus cos theta. Okay, and then what you're going to do is you can just plug in this r inside this, and then derive this r, and then plug in also into our dr over d theta. Okay. And then depends on in which theta you can evaluate the tangent. Okay. And similarly, you can also get the horizontal and vertical tangent, right? We can also locate the horizontal tangent. horizontal tangent when dy over dx equals 0, which means that dy over d theta need to be 0, and dx over d theta is not equal to 0. We can also get the vertical tangent. That is when the dx over d theta is 0 and dy over d theta is not equal to 0. So by evaluating this dx over d theta, dy over d theta, we get our equations. However, if you have some certain point and you are maybe curious on how the ratio will be, and you are using limit, and when using limit, you can remember when using limit, maybe theta to some angle, and maybe you have maybe dx over d theta, this may be some value. Maybe this will be resulting, or this is dy over dx, okay? Maybe resulting 0 over 0. Okay. So to solve this, you can directly use the L'Hopital rule. Okay. Some cases happen in the vertical tangent, and then you need to analyze using the L'Hopital rule. Okay, so this is actually first method to apply by, let me just make this box here. Let me write this is the first method, okay? So you can directly approach using this formula. However, the tangent is actually not different from parametric approach, like the first one we have. So instead of taking this formula, and maybe you try to memorize this formula, which I'm not suggesting to memorize, you can just go by just a regular parametric, okay? And then solve by parametric. So if you have the x r cos theta, okay, first you can exchange r with your known equations that may be given in the information. For example, if the r is 1 plus cos theta, so let's just approach 1 plus cos theta and then write in terms of this. And then we can have at least cos squared theta like that, right? And then the same way we have y is r sine, so we have 1 plus cos theta sine theta. And then we can also write here like that, okay? Or even you can write in more simplified, okay? The next thing is we apply our dy over dx and then using our parametric approach directly, okay? Like the usual parametric calculus. And each of this you can easily derive, okay? And then put into these equations. So this will turns out to be and then depends on which theta it will be, you can plug in the value and then you will have the tangent, okay? The result will be equivalent with our approach in polar in here, okay? It's the same method, okay? What we did here is actually we derive, in general formulations, we derive directly and taking the product rule, right? Taking the product rule and then put into our general formula that you can always use in any condition of polar. Actually, it's not pretty difficult to derive. I mean, if you know how to convert the x and y into the r cosine theta and r sine theta, and then you can put the equation and then you can derive each one of this. You can derive using the product rule, or maybe I'll write product rule. So if you, in case you wonder how that happened, this is product rule. Right. If this is FG okay. So this is from product rule of each of x and y. Okay. So you can always, if you forget like which one is plus, which one is minus, you can always do this, but of course, sometimes okay, there are some, I'm not sure, maybe some habit, okay, some habit. If you write x first and y, and then you write the already x, but you put x in the top and y in the bottom. So be careful on that. Okay? Okay, so this is the first method. The second is just using the regular second method, just a regular parametric. So exchange the r with some known functions that may be given in the informations, and then each of x and y derive and put into the tangent. Okay. Now that's the tangent in the polar. Okay. Now we move to next sections, which is the conic sections. We will focus at least three subsections, which is parabola, ellipse, and hyperbola. I would like to give you more geometric definition of all these three, because I think mostly you already know how to differentiate from the equation itself. Right? Okay, let me just wrote some introductions. So conic sections. So first of all, why the name is conic, like why it has cone. So of course it is related to the cone itself. So let's draw a cone. And let me draw two cones so we can have much more clear definitions. Okay, let's say that's our cone. Okay, if we slice horizontally, you will see a circle in the cross sections, right? Circle shape of circle. But if we have adjusted the slice, maybe tilted a little bit, maybe having some slope like this. So we slice the slope. Can you imagine? It will have some shape like that, and this is what we call an ellipse, right? And when we have slicing from this sides going down, okay, and then also slicing the base, okay. If we connect this, it will be a parabola. Okay. And then if we slice vertically and then crossing most of the sides, say from here, it will have two sides of, looks like a parabola, but it has two sides, and it has certain curve in the shape. We call this is the hyperbola. I'm not sure whether the GeoGebra has some visuals on the conics, especially how to slice from the cone. But you can try to check in GeoGebra if you have some. I haven't checked. Maybe later I will check. Okay, so these three will be our main discussion. And let me write in the right side here. That is the parabola. What is a parabola? Of course, we already know the functions, the equation itself, right? When we talk about y equal x squared, we know that that's a parabola, at least, right? Or y equal 2x squared plus something, it's still a parabola. We say it's parabola. But in a sense, before we get this equation, how do we define parabola? How we are defining the parabola? So we must have some set of fixed definitions at the beginning to know what is the shape of parabola. Okay. So let me draw some illustration on how we get this this idea of parabola. Okay, let's say we have maybe here. Let me just draw the parabola first to give you the idea. Okay. Okay, well, let's set some points. Okay. I will set some points here, which is called F. Okay. And I will have a line, the blue line on the bottom. I will call this blue line directrix. Okay. So if we have these two sides of fixed point, what parabola means is the parabola is a set of points in a plane that are equidistant from a fixed point F and the fixed line is called directrix. Okay, so that's in a word, but I think it's easy if we look on the graph. Okay? So the idea is if we have F and then we have some distance to points, any point in the parabola. Okay. So I think I can draw the line, just a line. Draw from here to here, and then from this parabola, another line connecting to directrix. This line will be an equal distance line. The same way, when you have another line, maybe here, and another line here, this should be having the same distance to fit in of what parabola is. Okay, so actually, if you're looking clearly on the drawing, you cannot really draw just a curve, but you need to make sure that the curve itself has the same distance as in the from focus and the directrix. Okay, so that is the parabola. And now from this idea, we can move this graph into our Cartesian x and y axis, and let's try to at least see how we can get the basic formula for the parabola. Okay. Let me make it a little bit down here, maybe here. So I will move to the x and y axis. So this is x, y, Cartesian, and then let me draw another parabola. Okay, I think that's okay. And then put another line, maybe around here. Okay, so that this will be our directrix, and this will be our focus here. Let's say this is our f. Okay, and let's say our f is at let me write here at 0 p. So it's p here. Okay, so the other sides should be negative p, right? In terms of the general x, y axis for parabola. And then let's maybe it's a different color. Let's connect to some random number or random points in the parabola. Let's say the point P, the big P, okay, that's small p. Okay. Okay. Now this is y, right? And this is p, small p, as in the distance. Okay, if we set and take the triangle, this triangle, we can get the distance from f to the parabola, right? From f to the parabola. This one. Okay, so we call the distance of pf or fp. This will be the Pythagorean x squared plus y minus p. Okay, let me just write the triangle. So this is x and this is y minus p, right? This is also p, right? Here. Okay. Now, based on the definition that we already set up, that the distance from f to the parabola and parabola to directrix should be the same distance, then this should be, let me just write the x squared plus y minus p squared. This should be the same as the distance from the parabola to a directrix, which is y plus p, right? Y plus p, okay? But let me write in the absolute value here to know that we are concerning the distance, okay? So the positive value. Okay, now to solve these equations, we can remove the square root by simply square both sides. And then we can remove p squared, remove y squared, remove, and then we get the value, or the equations is x squared equal 4py. So we call this our parabola with this is parabola, okay, with focus 0p and directrix y equal negative p. So then, if you have y equal x squared, based on these definitions, we can write this in terms of this, right? So we can have, if we would like to have, like, having a 4p, then the p should be 1 over 4 to make it into our x squared, okay? So that's actually what we are doing, is we just name some property that is defining the geometric shape on parabola, which is the geometric shape will be based on this p value. It will be determined which one is our focus, which one is our directrix. Okay. So the same way, we can have y squared equal 4px. We rotate the parabola, right? So this will be parabola with focus p0 and directrix x equal negative p. And of course, this is based on when you have the center or the vertex of the parabola is on the origin point, right? On the origin point. Somehow we can also shifted the parabola, change the center. Like for example, we can also change, like for example, like this. Which means its center is changing to 1 and negative 2 instead of 0, 0. Okay. Or the center or the vertex or the vertex is shifted. Okay. Because both of this is on, like for example here, the vertex is 0, 0, and the other one here, maybe this is also 0, 0. And depends on the equation also, you can multiply with the negative and then it will be mirror. Okay, it will be mirror. Okay. Maybe if you mirror, this will be the mirror. Okay. So x squared minus 4 pi y can be also mirror like that. So at least when we are in conic sections, when you are dealing with the sketching the graph, the important point in sketching graph is to determine the focus, the directrix for parabola. And then at least you can try as much as you can to make the distance from focus to parabola and parabola to directrix always the same on every point. Okay. At least you know how, okay? But of course, if you probably if I give you those questions in exam, and you, maybe you just draw roughly, what I need is you roughly mention about the focus and directrix. Okay, at least that is enough. Okay, at least that is enough. Yes. How's focus? Focus here. Okay. How do you know?
So yes.
It depends on equations. Depends on equations. Okay. It's always behind the vertex. It's always behind the vertex. And directrix is always in front of vertex. And as the definitions, that is, so the distance from here to here and the distance from here to directrix should be always the same on every point. Okay. Distance from focus to parabola, the same as parabola to directrix. Okay. Okay, any other question? Okay, you can stick to this just to formula for parabola. Okay, so let's go to the second shape. Or do you still need to write something from here? Or it's over? It's okay. It's okay. Okay. The second one is the ellipse. Okay, let me just draw some nice and round like that ellipse. Okay. Now the idea of ellipse, okay. The idea of ellipse is when you have we call another focus here, F1 and F2. When they are connected to the ellipse in a line, let me draw the line for you. Maybe from here to here, maybe a little bit far from here, maybe here. And then we have another one. Let's say this is our random point P in ellipse. The sum of the distance, okay, so PF1 plus PF2, the sum of these two distances should be equal to a constant. Okay. So if I draw another one, maybe with green one, maybe from here, and then here. Okay, this is also another P. This is also the same constant. So if we add these two lines, it's always the same constant. maybe another line. This also same constant. Okay. Okay, let me draw another ellipse so that will be maybe clearer. Okay. Let's say we have an ellipse inside the Cartesian. And then let's set our focus maybe here and here. And set into some value C, positive, negative C. And then set to some P around here. And then let this is equal constant, let the sum of distances from a point on ellipse to foci or to focus be 2a. Let's this is be 2a, that is greater 0. Why there are 2a? Because you will see in the equations, if it's just a, then it will be the equation will be something half, so it should have something to make it equal. But let's just see first here. So if we take PF1 plus PF2, this should be equal a constant to A. Okay. And then from the equations we can have some distance formula for each one of this. Okay. To help solving this equation or simplify these equations, I will take this take to the other side. And then square both sides. Okay, so we will have x squared minus 2cx plus c squared plus y squared. Okay, then equal 4a squared minus 4a and the square root x plus c squared plus y squared plus x squared plus 2cx plus c squared plus y squared. Okay. Okay, we can eliminate some of this. Y squared we can eliminate, c squared we can eliminate, and then x squared we can eliminate. So we will have 4a squared minus 4a this is 2cx, so it's 4cx. 4a squared minus, okay, let me just write 4cx like that. And we can remove 4, okay, and then we can have a squared plus cx. Okay, squaring one more time to remove the square root. So we will have a square and then we have a squared minus c squared in a group of x squared, and then plus a squared y squared, and then this will be cancelled, right? Let me just write okay. Now we have this equations. Okay, from the triangle, the length. Okay, let me just draw the triangle here. This length, let's say it's 2c. It's less than 2a, right? It's less than 2a. So if you plus this 2, these two sides, if you plus, it will be greater than the base, right? Okay. So based on this, we can write down that say 2c less 2a, then c is less than a, and therefore the equations here will be positive equations, right? So to simplify, we can let some other variables, let's say b, this will be in these equations, okay? And then we can rewrite our equations and then we can divide by a squared b squared, and then we have which is our general equation for all ellipses that is having form like this, right? Because there are at least two kinds of ellipse, right? And then we can find the intercepts. Okay, we can find the intercept that is actually equal with A. So this is A0, and this will be negative A0. And also the y-intercept, we found that this will equal with B. So we know that this will be B, this will be C, and this will be A. So if you want to look on what it looks like, we at y equals 0, x squared equal a squared is 1, so x squared equals a squared. So x is plus minus a. And we called the line for the horizontal line. So if we have the ellipse like this, okay. Okay. The line that has longer we call the major axis, and the smaller one we call the minor axis. Just some name or how to name the terms on the ellipse. Okay, let me write the conclusion and then we can have short break. Okay, the conclusions is maybe in the next page. Let me write first and then we can look back to take some notes if you want. So the first one is this, where the A greater B, and we have the focus on plus minus C. And the vertices is plus minus A. And we have another one. This is A greater B greater 0. So this will be for this ellipse, and this will be for this ellipse. Okay. And how you write is actually, it's up to you. Okay, because sometimes you write the same A, B, but different interval here. B greater A is the same. It's the same. Okay, so we can have short break. Okay. Okay, so let's continue a little bit. And maybe give you an idea on how we can use this formula to at least sketch or determine the equation of ellipse. Okay. Okay, if we have the 9x squared plus 16y squared equal 144, Now we can simplify this equation and take this. Let's multiply all by 1/44. Then this will be 9x squared. Let me just write first. And this equal 1. So this will have x squared is 16 plus y squared over 9 equal 1. Okay. So we now have a squared is 16 and b squared is 9, or we can have this in terms of plus minus 4 and b is plus minus 3. Okay. We can have also directly from these equations is the c is plus minus square root of 7. Okay, based on the value, okay, we can sketch the graph. Because a is greater b, so it should be having more in horizontal, right? So, okay, for convenience, let me just draw the ellipse here. Okay, maybe around there. So it should be 4, 0 here, negative 4, and this will be 0, 3. And this will be 0, negative 3. This will be this negative square root of 7. This is square root of 7. Okay, at least you mentioned this, or mentioned in terms of focus, will be plus minus square root of 7, 0. I think it's already cover all the important things in ellipse. Okay, that is if we have the equation. The other question that maybe a typical question in conics is we are given the points and we need to know which are the equations. So another example, given ellipse with focus and vertices. Find the equation, find the ellipse equation. Now we have the foci or focus. So focus is C, right? So C is 2, vertices is A. So B we can get from B squared, A squared minus C squared. This will be 9 minus 4, which is 5. And we know that this is ellipse that has this shape. So it's more elongated at the vertical axis, okay, because of the foci is on 0, 2, right? Vertex is on 0, 3. But it's actually, well, you can write like this, but I think it's better to write this B. We need to keep consistent. Okay, sorry about this. So this should be or maybe just write like this. Okay, I hope you still get the idea here. And then we can write that the x squared is with 5, and then y squared is 9, and this equal 1. Because we take the vertices here, which is A. This is plus minus or 3, or maybe just mention this is 3, negative 3. This is square root of 5, negative square root of 5. And in between here, this is 2, and this is negative 2. Okay. So we can write the equation as this. Either way, if you write in terms like maybe you take this as your V and you write a little bit different formula, as long as you're consistent and still take the same definition, I think that's still okay. Still okay. Because I believe in your high school you have a maybe a little bit different set of A and B, which are the fixed point. Okay, I'm talking about this. Okay, so you can take this back to A and B and switch the interval B and make it a consistent, and also this will be a different, and maybe it's B. Okay. But if you want to take the same approach as the textbook, you can take this. So whenever the ellipse is elongated on the horizontal, then you have x squared over a squared. But when the ellipse rotated, elongated on the vertical, you get x squared and b squared. Okay. Okay. Now I think I can move to the other sections, which is the hyperbola. So hyperbola has some similarity with ellipse in terms of definition. The difference is when ellipse is having the sum of the two lines, the hyperbola is having the difference or subtractions. Okay, so if we have let me just illustrate quickly on the hyperbola. Maybe around here. Actually, it still looks like a parabola because I think because the fixed curve on this apps. Hyperbola should have more. It's more like more. The curve is not really curvy. But let's say that this is hyperbola. Or let me just draw more clear on the hyperbola. It's more like having like that. And then similar approach with ellipse, we have behind the vertices. Now the vertices seems they are in two parts, right? So we have the first focus and then the second focus. Okay. We can take some number C, so plus minus C for the focus. And then let's say we have a point here, or maybe on the left also fine, but the difference in this is equal or constant. And I think hyperbola also frequently used in some physics. I think chemistry also, some chemistry. I think also in economics, also it can be appear. Okay, so instead of sum, we will subtract. So we will have the okay. And then similar to the ellipse, so similar to ellipse, we can have the sum for relations okay. So instead of plus, it's a minus. Okay. And how you prove that is similar with ellipse. So you take this distance and take this approach, and you mention this distance and this distance. Okay. C squared is a squared plus b squared. Okay. And then the x-intercept is plus minus a, and y-intercept no intercept, right? Or no y-intercept. Of course, if you plug in x equals 0, you will get the y squared equal negative b squared, which is actually impossible to have. Okay, to analyze the hyperbola from here, we can write down that x squared over a squared is equal 1 plus y squared plus b squared, which is clearly, we see from these equations that x squared over a squared is greater than 1, right? It's greater than 1. And it shows that x squared is greater than a squared, which define this x as square root of x squared is greater than a. So we have x is greater or equal a, or x is less equal negative a. This means that we have two sets of hyperbola, which are illustrates in this graph. Okay. Okay, so if we draw the hyperbola, okay, there is another set of parameters that we can also conduct to make sure that our hyperbola is drawn correctly. And we call this is the asymptote in hyperbola, which are, this is BA over X, this is okay. So if we have x squared over a squared minus y squared over b squared equal 1, this has focus plus minus c 0, and then c squared a squared plus b squared, and then the vertices plus minus a, and asymptote b over a x. Now the hyperbola also can be rotated, and it can has also two branches. Or maybe let me draw the asymptote. So it's better to draw the asymptote first before drawing the hyperbola, if you want to be more precise and sketching correctly, because this will give you the idea on how the hyperbola will exist. And their asymptote will be just the reciprocal from the original one. So this will be y squared If you still remember the idea of the slant asymptote in the calculus 1, this is actually same as we can also consider it as a slant asymptote. I think if you want to have like maybe more proof on how we can make sure that this is B over A, if you want to make sure, maybe if you feel that this will be maybe confusing to use the variables, maybe you can take some actual hyperbola equations and then you can take some approach within the slant asymptote, And to find the slant asymptote, remember that you can take the limit and make this like getting smaller and smaller and smaller. Right? Okay, I think we can move to some examples. Okay, so the idea is, if you have the questions, the first thing is you need to make sure which one is our hyperbola, the first one or the second one. How do we tell? We can tell from the focus, or we can tell from the equation. If this have a positive x squared, negative y squared, this should be this first one. If we have y squared and a negative x squared, this should be the second one. Okay. Now, if we have the example, we have the 9x squared minus 16y squared equal 144. It's the same or similar equation with different plus minus, and we have to sketch the graph. Okay, let's say sketch the graph. So first we can divide by 144, and we will have x squared divide 16, and since x is positive, y is negative, we will have on left and right hyperbola. So we can draw. Okay. At first, maybe we can tell the asymptote. It's plus minus 3 over 4x. So A is 4, B is 3. Right? Okay, so 4 maybe around here. 4. And C will be 16 plus 9, it's 25. So C is 5. Okay, so 4, maybe 5 is here, and another 5 is here, right? And maybe the asymptote is there, and the other one is around here. Okay. As long as you mention this, all the important points on the hyperbola, I think it should be okay. And then we can mention this is 3/4. This is negative 3/4. Okay, so far we all having an example and some illustrations on in the center of the origin, right? Either in the ellipse or in the parabola. The vertices on the origin, right? Parabola. Hyperbola, it has the cross section for the asymptote is on the origin. So if we shifted the graph, it was shifted to the center, right? Shift to the center. Like you have circle, you can also shift this circle. So for example, if we have 9x squared minus 4y squared minus 72x plus 8y plus 1, 76 equals 0. Now the question is sketch the curve. Okay, now we need to solve the equation first. We simplify and find what's the hyperbola equations. Okay, so we can simplify and then take the complete of the square of this. So we need to plus 1, and then this is plus 16, and then this should be plus 4, and then minus 1 for 4, right? Okay. This will turns out to be y minus 1 squared, and then 9x minus 4 squared, and this will be 36, right? 36. Okay, and then we can simplify. Right. Okay. Okay. Now we have these equations. Now we have y is positive, x is negative, so we will have top and bottom hyperbola, right? And now we have shifted, right? Shifted. So shifted from 0, 0 to 4, 1, right? Okay? It's shifted. In terms of hyperbola, what is being shifted? It's the center in which the asymptote is crossing, right? Or that's the origin point. We shift it to 4, 1. And then let me write that a squared is 9, b squared is 4, and then c squared is the sum of 9 and 4 is 13. So the focus, if it is origin, the focus will have plus minus 13. But since we are shifted, so this is the original one, and then it's shifted 4 times or 4 units x. Okay, 4 units x, so plus 4, and then 1 unit. So 1 plus square root of 13, or let me just write into two points. Okay. So this will be the new foci, okay? The new focus. So you can use the shifted one as your movement. How many units you will be moving. So 4 means 4 units of x and 1 unit of y. So we need to just plus into our foci, original foci here, and this is the new one. And we can do for all the things. Like for example, the asymptote, we can have asymptote. Usually, this is just 3 over 2x, right? Originally, in 0, 0. Well, since we are on 4, 1, so what we are going to do, we just change the y and x. This is plus minus, okay? And of course, it seems that it's difficult to draw, but as long as you you know the default sketch of hyperbola, we can just illustrate and sketch and mention the point. So the new one will be on 4. 1, 2, 3, 4, and 1 will be here. So this will be the where the asymptote is crossing. Here, and the other one will be here. Okay, and then you will have maybe around the vertices should be on A, so this should be 4. This is 4, 1. So it should be 3, right? Should be 3 plus minus 3, and the other one is plus minus 2. So 4, 1 plus 3 for y will be maybe around 1, 2, 3, maybe around here. This is 4, 4, and 1, 2, 3, maybe around here. Okay, maybe this will be the hyperbola, and the other hyperbola will be here. Okay, And the asymptote, we can write the asymptote. This will be the y negative 1 negative 3 over 2 x minus 4. This one is the positive 1. And then what else? The foci maybe around here. Focus is 4 1 plus square root of 13, and this will be 4 1 minus square root of 13. Okay, at least that will be the case. And it will be the same when you have the ellipse, you have the parabola. What you are doing is simply change the center or change the vertex. Okay? So for example, like this one here, we are going to shift from 0 0 to 4 1. Okay. The ellipse also, we can imagine ellipse. We have shifted the ellipse. So the center, that is the origin, we shifted. Okay. Okay, any questions? Okay. So this is shifted conics. We still have one small part on the conic sections, but in terms of polar, that is related to the Kepler's law, how the orbits moving. Okay, if there is no questions, let me go through. So I will have some feedback for you. So let me go by here. So you can scan the QR code if you haven't. And we will play some little game. Okay. Okay, we will have some feedbacks. I would like to know like which one you are having difficulties, and also I would like to know maybe the time limit. For example, if you have a difficult question, what will be the time you need to solve it, and it will be considered at least for your exam preparation, like what kind of question that I can arrange for you. Okay, and later please use your student ID so that I can know your progress, okay, from here and until later. Okay. If you want to join, you can join through the website menti.com and use the code 15929554. Okay, if you're ready, I can type the sorry. Should be okay. Okay, get ready. So concave upwards. Okay, concave upwards. Concave upwards is related to which part? I hope the time is okay. Have you still remember about the ln? How to derive the ln? Around 1 minute 40 seconds. Five seconds. Remember, in parametric, you need to be careful on the second derivative. Second derivative, careful to derive. Okay, thing nicely done. Okay. Okay, good. 41, who is 41? Oh, okay, 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 nice. Okay, next question. Okay, let's go. 3, 2, 1. Okay. Find area enclosed by parametric curve. Okay, so this is still parametric, and not polar. Still parametric. And please write the answer in a fraction form. Okay? So do not write in decimal. Write in fractions like 1/2, 2/3, something like that. And again, I hope the time is okay. minute. Around 1 minute. Okay. 55. Idea is to check the interval first, which theta is on the given information to find out the p. Okay. Some of you get correct. Okay. Sorry. Okay. Okay, good. Okay, one more question. Okay, I hope enough fun. Okay, I hope it's also not too complicated to evaluate, especially using the angle. Okay, there's still one last part that could get just some comments. So of course the time limit in this small quiz is just to check whether the time is okay or not. Of course for the exam it will be, time should be extended.